So here we're going to go over a 30,000 foot view of curve sketching. And so we've got the key ideas here. So whenever you're asked to graph this using the key ideas, this is what I'm talking about. So how to sketch a function without a calculator, consider the following steps. Step number 1, find the domain of f. How do we find the domain of a function? Well, first thing you got to do, look for the bad values, the values that are not in the domain. Once you know what's not in the domain, you take those out and whatever you have left, that's what your domain is, right? So examples that things that you might not have in your domain, we take a fraction. Dividing by 0 is a no-no. It's been a no-no for a while. So when you're talking about rationals, set the denominator equal to 0, and you'll figure out where your function's not defined at, right? Okay. Also, when you're doing a square root, what's bad with a square root or even indices? So we have an even index like square root, fourth root, sixth root. Well, we cannot take the square root of a negative number. So how would I get around that? Well, if I had like square root of x plus 2 or whatever, I'd take whatever's inside the x plus 2 and I'd set it to be greater than or equal to 0. And that tells me what values of x qualify. Also, natural log. Now this could be any base. I just picked the e base. You could have log whatever, okay? But what values can I not do here? I can't have 0. I also cannot have negatives. You think about the natural log graph, it looks like this. Never can you plug in an x value of 0, and you can't plug anything in for negative. Try to do it, your calculator will get angry with you, okay? So we don't deal with complex numbers in here. That would be a complex number scenario. All right, once you have the domain of your function f, step 2, find the critical values of f. How do I find critical values of f? I take the derivative of f, set it equal to 0, or where it does not exist, okay? Easy enough to find a list of the critical values. Once I have the critical values, then I want to find all possible points of inflection. And to find points of inflection, all I got to do is set the second derivative equal to 0 or where it does not exist. And this will get me a list of all the possible points of inflection. Number 4, I want to find all vertical asymptotes. So how do I get a vertical asymptote? I just take the denominator, set it equal to 0. If there's no denominator, like say it was like f of x equals x squared plus 1. Guys, the denominator here is technically 1. Guess what? 1 can never equal 0. So are there any vertical asymptotes for the parabola? No, there are not. However, say you had this scenario here. Well, I would set the denominator equal to 0, solve for x, and I would find x equal to 1. So I'd have a vertical asymptote x equal to 1 there. Okay. Now, step 5, I want to find all the horizontal asymptotes. How do I find horizontal asymptotes? I do this by calculating the limit. The limit as x goes to negative infinity of f of x, and the limit as x goes to infinity of f of x. If you think about horizontal asymptotes, this is what happens to the function as we go out to infinity, right? As x approaches infinity, maybe we have some horizontal asymptote here. And not only do you care about this way, but you also care about the left-hand side as x goes to negative infinity. You might have a different horizontal asymptote going that way, okay? Logistic curve is a very common example of that. So we take a left-handed infinity and a right-handed infinity there. Now to determine the end behavior of f, you literally take infinite limits here, okay? Cool. Number 6, we create a number line that has the critical values that I found in number 2, all the possible points of inflection, and then vertical asymptotes that you found, okay? So create a number line, for each of the sub-intervals, right? So I want to figure out, is it increasing or decreasing? How do I know if a function is increasing on that sub-interval? Well, if the derivative is positive, the first derivative is positive, then we're increasing. If we're decreasing, that means the first derivative is negative, okay? Now, concave up, concave down, so that's like this or like that, right? Versus decreasing and increasing there. Okay, so concave up, we look at the second derivative. Concave up is like a cup. When we're positive, we're smiling, so positive derivative going up like this. Concave down has a negative derivative for the second derivative. And, hold up, went a little too far. So negative concave down is like a frown, just like that. Okay, so if you had a scenario where it was like a decreasing function, but it was concave up, what would that look like on that interval? Well, you'd be decreasing, but you would be decreasing in a concave up fashion, so maybe it would look like this. Okay, so it kind of tells you how to draw the curve from one critical point to the next critical point or point of inflection, whatever it is. Okay? Number 7, I want to evaluate f at each of the critical points and the possible points of inflection, and plot those points along with the x-intercepts and y-intercepts. Now, how do I get an x-intercept? Go back to college algebra. You set y equal to 0. So if you had like y equals x squared plus 2x, to find the x-intercept, I put a 0 in for y. Okay, and then I solve for x, right? To get the y-intercepts, I set, well, if I set y equal to 0 for x-intercepts, for y-intercepts is the opposite, right? I set x equal to 0, okay? So I have y equals x squared plus 2x, right? If I put x equal to 0, then I have y equals 0 squared plus 2 times 0, so y equals 0 there, right? Okay, so not too bad. You can go back to college algebra videos I have on my YouTube channel if you're having trouble finding intercepts. Just search for how do I find x and y intercepts. All right, if you can get the x-intercept by factoring, so factoring or by quadratic formula, that's great, okay? If you can't do it by using quadratic formula or factoring, then just use your calculator and find the 0. Just to give you an example here, say you had some weird function. Let's see, that's not too weird. Let's do something really weird, like that's ln. That's okay, whatever. ln x, and then let's just say plus x, okay, whatever. And so I want to know, where does this thing cross the x-axis? All I do is I go second calc, and I find the 0, number 2 there, and then I get on the left side, and then I go to the right side, and it tells me, okay, here's the 0 at 0.567, okay, whatever. So you can use technology there. You just tell me I used my calculator at that point. Uh-oh. Come on, get out of this. Did we lock up? What is going on here? All right, there we go. So, step 8, we connect the dots with the appropriate concavity. So say, you find the, evaluate the function at the critical values and points of inflection. You've got all these dots, all these critical dots or whatever, okay? So at this point, and maybe this is the intercept or whatever, those are the intercepts there. And then hey, look, the function is decreasing and concave up here, so I connect it like this. And then it's increasing and concave up here. And then, here it's, ooh, that's kind of weird. I'd have to have some other point, right? So So maybe it changed concavity, now it's concave down, and now we're concave up and increasing there, whatever. Okay, so this part here tells you where how to draw your curve, okay? And we just connect our dots that we found in step 7, okay? So connect the dots with the appropriate concavity, and then sketch any lines that are vertical or horizontal asymptotes. Like say you have, you know, I don't know, some rational function. Well, you know that there's a horizontal asymptote here, and then maybe you got a horizontal asymptote here. And so sketch those with dashed lines. That's what I'm talking about there. And you can say like x equals 2 there, you know, and y equals 0 for that dashed line there. Okay? So hopefully this video kind of gives you more of a 30,000 foot view of how to graph a function f. Let me zoom out in the same spirit of the 30,000 square foot view or foot view. That way you can see every step all in one. So this kind of encompasses a step-by-step how to graph a function without your calculator, which is actually pretty exciting that you don't have to have that stinking thing. You can actually use calculus to graph it and get a very good sketch.